Hello everyone, this is a video in abstract linear algebra, in particular about what I call eigenstuff. So this is a video about eigenvectors, eigenvalues, and eigenspaces, which are some very important concepts in linear algebra that actually have a lot of applications. And what we're going to do is explain what these things are and then how to find them. So let's get started. Here V is going to be a vector space over a field F, and T is going to be an operator, a linear map from V to V. Remember that LVV is the space of linear maps from a vector space V to a vector space W. So in this case, we're just going from V to V. We're going to be writing this operator in coordinates. So let's fix a basis of V. Here, V is going to be a finite dimensional vector space. So this is a finite basis. And A is going to be the matrix of this operator with respect to the basis B. We'll have some examples coming up. So hang on if you need a refresher on what that matrix is. But the question that we're going to start to motivate how to find and why do we care about eigenspaces is what is a basis of V that gives a the simplest matrix A for the operator T. Depending on what basis we pick, the matrix A may be super complicated or perhaps very simple. So we're trying to find a basis B that will make these matrix as easy as possible to work with. For example, take T to be the linear operator from R2 to R2, which is just 90-degree rotation counterclockwise. If I take B to be the canonical basis of R2, then E1 is sent by 90-degree rotations is sent to E2. 1, 0 is sent to 0, 1. And E2, it will be sent to minus E1. So that tells me that 0, 1 is sent to minus 1, 0. Therefore, the matrix for this transformation is this matrix, because remember that the matrix is built by the first column is the column of it represents where the first vector of the basis goes. So this is T of E1, and this is T of E2. So since E1 goes to E2, the first column is 0, 1, and since T of E2 is E minus E1, the second column is minus 1, 0. Now, this is not a very complicated matrix, but it is not, for example, a diagonal matrix, which would be a lot easier to work with. So is there a basis for this, for R2, instead of the canonical basis, that would make this even simpler? Well, we'll see. Now, let's have another example here. The transformation here is going to be also a transformation from R2 to R2. And in this case, the transformation that I have in mind is the reflection about the line x equals y. And that is linear. And with respect to the canonical basis of R2, well, we see that 1, 0 is being sent to 0, 1, and 0, 1 is being sent to 1, 0. So this is the matrix with respect to this, with respect to the canonical basis. But notice that in this case, there is clearly a change of coordinates that would make the transformation more transparent of what is actually happening, because the line x equals y is clearly fixed. So if I pick any vector on the line, those vectors are fixed by the transformation, while if I pick vectors that are perpendicular to the line, those vectors are flipped. So if I take my new basis, b prime, to be the 1, 1, and 1 minus 1, you can check that those two vectors are linearly independent. So they are a basis of R2. Then the matrix with respect to this new basis will be the following. This vector is sent to itself, so it's sent to 1, 0. And this vector in coordinates is sent to minus itself, so the coordinates are 0, minus 1. So the new matrix with respect to this basis is a lot simpler than this one, because this one is a diagonal matrix. And these matrices, for example, to take powers of these matrices, to multiply together with all their matrices, these are a lot easier to work with. So we've sort of won, and we've found a different basis where this transformation has a simpler form. Now, the vector 1, 1, as I said, the vector 1, 1 is special, but in fact, any vector in that line is special. So if I look at the span of that vector and call it u, what I notice is that this entire space is sent to itself. And that's what we call an invariant subspace. Similarly, this vector space, the space of the perpendicular line to the reflection line, that is also sent to itself. So V is also what we call a invariant subspace. Okay, so more generally, if I have a transformation, an operator from V to V, and I have a subspace U, a linear subspace, such that T sends that space to itself, inside itself, then we call U to be invariant under T. Notice that I do not require T of U to be equal to U. I just need T of U to be contained in U for that to be considered invariant. Here's an example of what's happening here. So for example, if I take the derivative map from polynomials over f to polynomials over f that sends a polynomial to its formal derivative, p prime of x, then you see there is a subspace, which is the polynomials of degree less or equal to n. That is invariant under derivatives, because when I take a derivative of a polynomial of degree less or equal to n, I get a polynomial that is of degree less or equal to n minus 1. So I get all of them, so I can take the derivative of the polynomials of degree less or equal to n. I actually get the space of all polynomials of degree less or equal to n minus 1, which is contained, not equal, but is contained in un. So this un is a linear subspace that is invariant under the transformation D. Here's a picture of what's happening when there are invariant spaces. I have a transformation T from V to V, and here is a space U that is being sent to U, not necessarily all of U, but inside of U. Now, when we have a space that is invariant and one-dimensional, then U will be the span of one single vector, little u, and this span is all the possible multiples of U. Now, if T of U is in the span, because, well, we are assuming that U is invariant under T, then T of U has to be one of these. T of U has to be some multiple of U for some lambda in F. In that case, we call U, little u, to be an eigenvector, and lambda to be an eigenvalue. So here's the definition of eigenvectors and eigenvalues. If I have an operator and I have a vector, a non-zero vector, so eigenvectors are non-zero. If I have a non-zero vector such that T of U is a multiple of U, then we say that U is an eigenvector and that lambda is the eigenvalue attached to U. So U is an eigenvector with eigenvalue lambda. So here is, again, the definition of eigenvector and eigenvalue. And notice that actually, if I have one eigenvector, I have a lot of eigenvectors, because if U is an eigenvector with eigenvalue lambda, and alpha is any other element of F, so alpha times U is some multiple of U, some multiple vector, then T of alpha U will be, well, T is a linear map, so the alpha can come out. So this is alpha times T of U. T of U, by definition, is an eigenvector, so T of U is lambda U. And now by the commutativity in F, this is lambda times alpha of U, alpha times U. So this means that T of alpha U is lambda times alpha U. So alpha U is also an eigenvector with also eigenvalue lambda. So if U is an eigenvalue, an eigenvector with eigenvalue lambda, then any multiple of U is also an eigenvector with an eigenvalue lambda. So what we say is that not just U is an invariant, is an eigenvector, the span of U is all of them. All of the vectors in the span of U are eigenvectors with eigenvalue lambda, so we call this an eigenspace. And in fact, we are going to call it an eigenspace with eigenvalues eigenvalue lambda. Okay, so that's our first instance of an eigenspace, not just one eigenvector, but an eigenspace such that every element in there is an actual eigenvector. Going back to our transformation from R2 to R2, which is the reflection about the line x equals y. Remember that this is the form, the matrix form for the transformation in coordinates with respect to the canonical basis. And but you see that the vectors 1, 1 that we found, that 1, 1 was invariant under this transformation, is an eigenvector. I can see it right here. If I multiply the matrix by 1, 1, I get 1, 1. So this is 1 times 1, 1. So 1, 1 is an eigenvector with eigenvalue 1. And v, 1 minus 1, which was one of the vectors in the perpendicular line to the line of reflection, if I act with the matrix A times 1 minus 1 is minus 1, 1, which is not itself, but it is minus 1 times itself. So it is, again, an eigenvector, but this time for the eigenvalue minus 1. So these are eigenvectors, but for different eigenvalues. This is for the eigenvalue 1, and this is for the eigenvalue minus 1. Now, we would like to be able to compute eigenvectors and eigenvalues for a given operator t. So this theorem is going to tell us exactly how to find them. Let V be a finite dimensional vector space, and t from V to V be a linear operator, so from a linear map from V to V, and suppose lambda is just some number in the field F. Then the following are equivalent. Lambda is an eigenvalue for t, if and only if t minus lambda times the identity, this is a new operator, is not injective, if and only if t minus lambda times identity is not surjective, if and only if t minus lambda times identity is not invertible, if and only if you know about determinants, whenever I have that an operator is not injective, that is, if and only if the determinant of that matrix, for any basis, if I write a matrix for that operator, that determinant will be 0. So this is, for example, equivalent to this condition. And the proof of this is the following. So suppose that lambda is an eigenvalue of t, then by definition, t of u is equal to lambda u for some vector u. There is an eigenvector with eigenvalue lambda. If I bring this to the other side, this is if and only if t of u minus lambda u is 0, and lambda times u, the scalar multiplication lambda times u, is the same as the operator lambda times the identity map times u. And this, I can put these together, these operators, this will be 0 if and only if t minus lambda identity of u is 0. So that tells me that we have an eigenvector u with eigenvalue lambda if and only if there is something in the kernel of t minus lambda times identity. Have something in the kernel, in the null space of this operator, is equivalent to the operator being not injective. And since this is a finite dimensional vector space we're talking about, then being not injective is actually equivalent to not being surjective, and is equivalent to not being invertible. Therefore, all these equivalent statements are going to help us find eigenvectors and eigenvalues. How? Well, let's try to find if there are any eigenvectors of eigenvalues for the rotation, for the 90-degree rotation, just to see if there is something we can do to put this the matrix for this map in a better basis. Well, I mean, you can see already that any line is being rotated, so no lines are being simply there is no space, no one-dimensional vector space, subspace, that is actually invariant under this transformation. So this is not going to work out over R2. So let's see how this actually tells us that I am right. So here the transformation in coordinates with respect to the canonical basis is 0, 1 minus 1, 0 times xy. And are there any eigenvectors of eigenvalues? Well, if so, then I can construct the operator t minus lambda times identity. T minus lambda times identity will be this matrix minus lambda times identity. So that is going to give me minus lambdas in the diagonal. So now this matrix, if there are any eigenvectors for lambda, then this matrix would have determinant 0. The determinant of this matrix is lambda squared plus 1. And if this is 0, then there would be a real number lambda whose lambda squared plus 1 gives me 0. So there are no real roots. So there are no eigenvalues over the real numbers. But of course, we know that this has roots over the complex numbers. So what happens if I upgrade this map to the complex numbers? Maybe I was just looking at it the wrong way by looking at it over R. And if I look over the complex numbers, something nice happens. So I'm going to look at the same operator, but over the complex numbers in 2 dimensions. So it's going to send ZW to minus WZ, that is a rotation of 90 degrees. And with the canonical basis in the complex numbers squared is still 1001, I still have this matrix for that transformation. Now, A minus lambda times identity still has this form, and it gives me that the determinant will be 0 if and only if lambda squared plus 1 is 0. So this tells me that if there are eigenvectors, it will be for the eigenvalues plus or minus I. So now I can try to figure out if there is an eigenvector for lambda equals I and an eigenvector for lambda equals minus I. Let's see what happens for the possible eigenvalue lambda equals I. If there are eigenvectors with that eigenvalue, they will be in the null space of this operator where lambda now is equal to I. So I can compute this null space. This matrix has this form now, and I can try to compute what is the null space for this matrix, what vectors are sent to 0. So I want x and y such that this times xy gives me the 0 vector. That gives me the first condition is that minus ix minus y is 0, and the second condition tells me that x minus iy is 0. And you see that in both cases, what it's telling me is that x equals iy. So I can actually tell, so if I pick y to be 1, then x will be I, and this vector is indeed an eigenvector with eigenvalue I. I can check, multiply my matrix times I1. It gives me minus 1 I, which is in fact I times my original vector. So this vector is an eigenvector with eigenvalue I. Similarly, if I pick lambda to be minus I, then I'm going to look at the null space of this operator for lambda equals minus I, so the null space of this matrix. And if you do the same thing, then you find out that there is an eigenvector with eigenvalue minus I, and that is minus I1. So what I've arrived at is that over the complex numbers, there is a better basis, which is the basis I1 minus I1. And with respect to that basis, the matrix for my transformation is diagonal, is I0, 0 minus I, which is much simpler to work with than this sort of anti-diagonal matrix. By the way, notice that the eigenvectors I got I1 and minus I1 just happened to be linearly independent, and they were able to make a basis. So, but what if I got some vectors that were not linearly independent? Then I will not get a basis, and I cannot change basis to a new basis and get a new matrix that is better. So do they have to be linearly independent? It turns out that they do. So let me prove that. If I have an operator such that lambda 1 through lambda m are distinct eigenvalues with eigenvectors u1 through um, then these vectors are linearly independent. And I remark again that these are for distinct eigenvalues, then they are linearly independent. So suppose for a contradiction that those eigenvectors are actually linearly dependent. And let k be smallest such that uk is in the span of the other ones. Remember that if you have a list of linearly dependent elements, then there is a first element, starting from the right, there is one element, at least one element that is going to be in the span of all the others. So let uk be in the span of u1 through uk minus 1. Then, since uk is in the span, then there is a linear combination of u1 through uk minus 1 such that uk is that linear combination for some coefficients in the field. Now, if I apply the operator t to this identity, t of uk is an eigenvector with eigenvalue lambda k. So I get uk is lambda k times uk. And if I apply the operator to this expression, since it is linear, what I'm going to get is u1 goes to lambda 1 u1, and uk minus 1 goes to lambda k minus 1 uk minus 1. So I get this expression instead. Now, if I multiply this expression by lambda k and then subtract 2, so multiply the line 1 by lambda k and subtract 2, then here I'm going to get 0. And over here, I'm going to get an expression of this form where the coefficients now are ai and then lambda k minus lambda I. All right. Now, k was smallest such that uk is in the span of u1 through uk minus 1. And that tells me that this is not possible, because this tells me that uk minus 1, that there is a linear dependence between u1 through uk minus 1. So, well, in particular, for example, uk minus 1 would be in the span of all the others. So that tells me that every coefficient here has to be 0. So this is 0, and all of these are 0. And by the way, all the eigenvalues are distinct. So these lambda k minus lambda 1, lambda k minus lambda k minus 1, those are non-zero. So that tells me that all the a1, a2 through ak minus 1 are 0. And if you go back to this identity, it tells me that uk is 0. But 0 is never an eigenvector, so we've reached a contradiction. And this proves that the eigenvectors u1 through um must be linearly independent. And as a consequence of this proposition, if we have that, if I have distinct eigenvalues, then the eigenvectors are linearly independent, that tells me that I can't have a lot of distinct eigenvalues, because if I have eigenvalues, I have eigenvectors. The eigenvectors are linearly independent, and I cannot have more linearly independent vectors than the dimension of the space. So that tells me that any operator has at most dimension of v distinct eigenvalues. So for instance, if I have the operator that goes from the complex numbers to the complex numbers in 2 dimensions given by this matrix, then I can try to figure out what are the eigenvectors. I can take a minus lambda I identity and see what the determinant of this is. And this has determinant 1 minus lambda squared. So there is a unique eigenvalue, which is lambda equals 1. So there is only one eigenvalue. So now, are there more eigenvectors? Are there eigenvectors for this eigenvalue that are linearly independent? I can try to find what are the eigenvectors for that lambda. So plug in lambda equals 1 here and find the null space of that matrix. The null space of this matrix is the span of the vector 1, 0. So it turns out that the null space is one-dimensional. I only have a one-dimensional eigenspace attached to lambda equals 1, and that tells me that in this case there is no basis of eigenvectors. So it is not always true that we will have a basis of eigenvectors. In some cases, even over the complex numbers, there is no such basis. And this kind of matrix may be the best I can do. Okay, so we might not have a basis of eigenvectors. However, every operator over the complex numbers does have at least one eigenvector. There is an eigenvalue, and therefore we have an eigenvector. This is what we're going to prove in this theorem to finish this video, is that every operator over a vector space over the complex numbers does have an eigenvalue. So we might as well assume that V is isomorphic to n copies of the complex numbers in coordinates. So I'm going to assume that we're talking about an operator from Cn to Cn. Now, suppose V is non-zero in V. Okay, so just take any non-zero vector V and consider the following sequence. I'm going to take V and then T of V and then T of V and then T, and then just do the composition of T n times and apply to V. Now, this is n plus 1 vectors, and Cn is an n-dimensional vector space over the complex numbers. These are n plus 1 vectors, so they have to be linearly dependent. That means that there are some coefficients, a0 through an, complex numbers, not all 0, that give me a linear dependence among these vectors. Okay? Well, also notice that I can't have that a1 through an are 0 and a0 non-zero, because if these were all zeros, that would give me that a0 times v is 0. And since a0 is non-zero, that would give me that v itself is 0, but I've assumed that I've started with a v that is non-zero. Now, if I take, I'm going to make this into a polynomial, p of z, a0 plus a1z plus anz to the n, then I am working over the complex numbers. And the complex numbers, thankfully, is an algebraic closed field by none other than the fundamental theorem of algebra. And that means that every polynomial can be factored completely. Every polynomial has a root over the complex numbers, but in particular, I can factor it completely over the complex numbers. So this polynomial will be some constant times z minus lambda 1 through z minus lambda m, where lambda 1 through lambda m are the roots, the complex roots of this polynomial. Now, if I apply t to this polynomial referred to this identity. So t in this polynomial, that gives me 0. And on the other hand, if I put t in here, that is z times t minus lambda 1 times identity, a product of t minus lambda 1 times identity to the dot t minus lambda m times identity applied to the vector v. Now, if this product applied to v is 0, then I can actually conclude that one of the t minus lambda I times identity is not injective. How? Well, let me just prove a lemma here to do that. And it's that if I have operators a and b and a times b, or the composition of a and b applied to v is 0, then one of the two is non-injective, because a times v applied to v is a times b applied to v. And we have two possibilities. Either b times v is already 0, and in which case b is non-injective, or a times this vector is 0, and b times v will be, if b times v is non-zero, then I have a vector w, namely b times v, such that a applied to w is 0. So in that case, w is in the kernel of a. So either v is in the kernel of b or w is in the kernel of a. And you can, using induction, you can prove the same thing for n operators that are composed with each other. And therefore, since this composition of operators applied to v gives me 0, one of them will give me non-injectivity. And if this is non-injective, then lambda I is an eigenvalue for t. And therefore, there you go. Then we have found that we have at least one eigenvalue lambda I for my operator t. So there is always at least one eigenvalue for my operators.